deep learning. You hear that term thrown around all the time, right? It's the magic behind your phone's camera, it's in our hospitals, it's everywhere. But what does that word deep actually mean? Is it, deep in some kind of philosophical sense? Or is it something a lot more straightforward? Well, let's find out. We're going to peek inside one of the most important black boxes in all of tech. Okay, so to get to deep learning, we've got to start with just learning. And this is where things get really interesting because it represents a total flip in how we've always talked to computers. See, for decades, programming was all about writing a perfect step-by-step recipe for the computer to follow. But machine learning, it completely throws that idea out the window. Check this out because this slide really lays it all bare. On the left, you've got your traditional computer program. You feed it some data, you give it the rules like a recipe, and boom, you get an answer. Simple enough. But look at the right. With machine learning, you give it the data and you give it the answers you're looking for. And you tell the machine, okay, you figure out the rules. You tell me how we got from A to B. It's a total reversal. Right, let's make this super simple. Look at this table. If I show you this, your brain pretty much instantly goes, oh, I see what's going on. The number on the right is just double the number on the left. The rule is y equals 2 times x. You didn't need me to spell it out. That is the goal of machine learning, to build a system that can do exactly what you just did, to look at a bunch of examples and figure out the hidden pattern all by itself. So, the big question is, how on earth do you get a machine to start thinking like that? Well, the folks who first dreamed this stuff up looked for inspiration in the most powerful computer on the planet, our own brains. And they decided to start small. They tried to build just one single digital brain cell, an artificial neuron. And this is where it gets really cool, and honestly, a little less intimidating. I mean, the human brain has something like 100 billion neurons. That's a staggering number. But a tiny little nematode worm, it has just 302. And with those 302 neurons, it does everything it needs to survive. It finds food, it avoids getting eaten. It's a perfectly functional creature. So that raised a really hopeful question. What if we don't need to build a whole human brain? What if we could just start with something simple, like a worm? So what does one of these artificial neurons actually do? Well, you can think of it as a tiny little gatekeeper or a decision maker. First, it gets a bunch of signals coming in. Then, and this part is absolutely crucial, it has to decide how important each of those signals is. It does this by applying something called a weight. The volume knob analogy is perfect here. It's literally turning the volume up on some inputs and way down on others. Finally, it adds up all those adjusted signals, and if the total is strong enough to pass a certain threshold, it fires, sending its own signal out to the next neuron in the chain. Okay, but let's be real. One single neuron isn't going to change the world. It's not very smart on its own. The real magic, the real power happens when you start connecting thousands or even millions of them together into a network. It's like going from one singer to a whole choir. This is where the actual learning starts to happen, and it all boils down to a pretty simple idea. Guess, check how wrong you were, and then guess a little better next time. At its core, a neural network has a pretty simple structure. You've got your input layer. This is where the data comes in, say a picture of a cat. Then all the way at the other end, you have the output layer. This is where the final answer pops out, hopefully the word cat. But everything in between, those are the hidden layers. And they're called hidden for a good reason. We don't program them directly, and it's often really hard to know exactly what's going on in there. This is the famous black box we're trying to peek into. So how does the network know if it's doing a good job? How does it know if its guess was right or wrong? Well, it uses something called a cost function. Don't let the fancy name fool you. It's literally just a score of how wrong it was. Think of it like a grade on a test. A really high cost means a terrible guess. You failed. A cost of 0, that's a perfect score, an A+. The entire goal of this whole learning process is just to get that cost, that error score, as low as you possibly can. The best way to picture this is to imagine the error as a giant foggy mountain range. Your goal is to get to the very lowest point, the deepest valley. The catch is, you're blindfolded. You can't see the whole map, but you can feel the slope of the ground right under your feet. So you just figure out which way is downhill, and you take a tiny step. You do it again and again and again. That simple process of always stepping downhill, that's what we call gradient descent. And that brings it all together. When we say an AI is learning, what's really happening is this. The network is automatically tweaking all of those millions of little volume knobs, those weights we talked about, over and over and over. Each little tweak is another tiny step down that error mountain, trying to find the combination of knob settings that makes the error score as close to 0 as possible and makes its guesses consistently good.
Okay, this is it. This is the core question we've been building towards. We know we need a network of these neurons, but to make it really, really smart, how should we build it? What's the best blueprint? Do we make it super wide, with just one massive hidden layer packed with tons of neurons? Or is it better to make it deep by stacking many layers on top of each other? And this lays out the two big schools of thought perfectly. On one hand, you have a wide and shallow network. You can think of this like a giant committee meeting where everyone tries to solve a complex problem all at once. Total chaos, maybe. On the other hand, you have a narrow and deep network. This is much more like an assembly line. The first layer does something simple, like identifying basic edges and colors. It passes its work to the next layer, which combines those into simple shapes. The next layer combines shapes into, say, an eye or a nose. Each layer builds on the last, getting more and more complex. Now, for quite a while, this was a huge debate among AI researchers. Wider or deeper? Which architecture had more raw power, more ability to understand really complicated patterns? It was a real tug of war. But over the last decade or so, the evidence started pointing pretty strongly in one direction. And we don't have to guess. Let's look at what the research says. This quote from a major AI conference in 2017 really nails it. Depth is more effective than width. It's pretty unambiguous. Going back to our analogy, they found that adding another station to the assembly line is a way more efficient and powerful way to get smarter than just cramming more and more people into that single committee meeting. And that's it. That brings us right back to where we started. Why is it called deep learning? It's not because it's having deep thoughts or pondering the meaning of the universe. The reason is actually much, much simpler. It's completely literal. Deep learning is just the name we give to AI that uses neural networks built with lots and lots of hidden layers. That's all it is. The deep part is describing the architecture of the network, its depth. It refers to the choice to build an assembly line instead of a committee. That's the whole secret. It's a design principle that just turned out to work incredibly well. So there you have it. We've peeked inside the black box, and the big secret behind the word deep isn't philosophical at all. It's architectural. Stacking layers on top of each other proved to be a more powerful way to build AI than just making one layer wider. Right now, depth is king. But it leaves you with a really fascinating thought, doesn't it? If this is the shape of AI today, what completely new shape will the AI of tomorrow take?